Okay, we learned this basic example and motivated the linear regression model. And this structure is actually pretty common in many economics. Like if you assume something is linear. So for example, let me give you two examples. So the demand or the supply function can be considered a linear function, then you may apply the linear regression model. So here, demand or supply function takes this form. Q is the quantity demanded, the demand or the supply, and the demand or supply is determined by the market price. If the price increases, then there will be less demand but more supply. So beta 1 captures the change. And if the price was 0, beta 0 is just the base demand. And beta 1 to beta 0 is the base demand or base supply that is not affected by the price. And beta 1 is how much the demand or supply changes when price increases or decreases, right? Of course, epsilon is the error term, so the noise in the demand or supply or in the data. And usually in this function, we are interested in estimating beta 1 because beta 1 is the elasticity of demand or supply. So how sensitive the demand or supply is to the price. That's the major parameter, the main parameter of interest in many demand or supply analysis. Like especially when you'd like to maximize your monopoly firm's profit, then demand elasticity is the only parameter you need to estimate. Something like that. Okay, another example now from macroeconomics. Keynesian consumption function. So in Keynesian macroeconomics, the basic one of the underlying assumptions is that the consumption, the household consumption, is a function of the income. So that means the saving and so the household adjust their consumption and income depending on their consumption and savings depending on their income. So when your income increases, consumption. So when you make like $1 more, your salary increases by $10, for example, $100. Consumption does not increase as much, right? Because some of the increment is saved for the future. So that's the starting point of the Keynesian macroeconomics. And in this case, beta 0 is the consumption, autonomous consumption. That is, this is the amount of the consumption you need to survive. So even if your income is 0, you have to you have to eat. You need a home to live, and you need some basic utilities should be paid. So that's beta 0, the basic consumption you need. And beta 1 is called the marginal propensity to consume, MPC. The marginal propensity to consume is exactly what I meant. When you make $100 more, if you, for example, if you found $100 bill on the street, you took it, and then are you going to consume that all or save it to the account? That's the ratio is beta 1, marginal propensity to consume. And beta 1, the marginal propensity to consume, is one of the most important parameter when you determine the effect of government spending. If you have heard about the multiplier effect, so when the government increases its spending by, say, $1 million, then GDP actually increases more than $1 million, right? Because when I pay $1 million, then the recipient will spend some of them, and then the second recipient will spend some of them, so then it will circulate more than and generate more than $1 million effect. So that's the multiplier effect, and beta 1 is the multiplier, related to the multiplier. So the higher the beta 1 is, the higher the effect of the government spending on GDP. So these are examples of the linear regression models. So you remember, if you remember when you remember these things from introductory or intermediate micro macro, then at that time exactly same structure applies. At that time in that textbooks, you must have been given the numbers for beta 0 and beta 1. So given those numbers, let's maximize the profit, for example, or given those two numbers, let's calculate the effect of government spending. However, as I said, like in practice, you never know what's the elasticity, what's the marginal propensity to consume. So theory has been developed like 50 years ago, but still new research is coming on the estimates of beta 1 elasticity for different markets, for different products, and beta 1 or like the marginal propensity to consume depending on like the situation. Like so. So estimation is usually more complicated. I'm not saying economic theory is useless, but they are important, but usually they are kind of clear, settled. But the data is more dirty, so there are still ongoing debates on like new methods coming out to estimate those parameters. Okay, so I gave you three examples for linear regression. So keep them in mind. Now we generalize our terminology. So the equation itself does not change. We are still doing the same thing. Basically, we are doing the same thing. The Y was cost, total cost, or demand, or consumption, household consumption. And X was either output, production output, or the price, or household income. So depending on the context. So depending on the context, you want to predict something out of something. Or input is X, output is X, Y. So when you observe X, you'd like to predict how Y will change. That's the pattern. And in general, Y is called dependent variable because Y is determined depending on X, determined by X, so it's dependent. But X is independent. So household income, price. So you can just change that and imagine different things like how much you produce, what would be the price, and what's the income. So X is called independent variable, or I prefer explanatory variable better. So it explains how Y is determined. So X, sometimes I prefer call this explanatory variable, but more officially, it's more common to call this independent variable or regressor. Okay, and just I'll call this X usually. And beta 0 is mathematically it's the intercept or the constant term. Intercept, right? In the linear function, intercept is the part that does not interact with the variable. So additive part. And what beta 0 is the slope of this linear function or the coefficient of x. So when x increases by 1 unit, y increases by beta 1. And epsilon is the error term or the disturbance term or noise. So different fields use different terms, but usually it's pretty intuitive, straightforward what it refers to. So as I said, the final goal would be to predict the value of y on the basis of x, right? So their relationship, finding their relationship is what we want to do. Then also finding the relationship means on graph on the scatter plot is to draw one trend line, straight line, going through those observations. So this is the result. Actually, this is the result of the regression using those data. 12 observations imply this trend. Then it's clear. As you increase your production, the total cost would increase at this rate, at this slope. And so then how can we interpret this? So first, look at this. Even if you produce nothing, produce zero, you have to, your total cost is estimated to be, say, nearly 8, 7 something or 8. So that's the fixed cost. Even if you do not produce at all, still you have to pay fixed cost, right? That's this much, beta 0. That's the meaning of the intercept, the fixed cost. And the slope is beta 1. So when you increase output by 1 unit from 4 to 5, 1 unit, then y increases from here to here, here to here. So that ratio is the slope. That's beta 1. And the deviation of a point on observation from the trend line is the error term. The error is the difference between what the truth is and what you observe. So your observation is contaminated by the error term this much. So your error could be negative or could be positive. Some observation could be above the line, some could be below the line. So negative or positive errors can happen. Okay. So in summary, the parameters we would like to estimate are beta 0 and beta 1. The fixed cost and the marginal cost. Or like say usual beta 1 could be interpreted depending on the context, like the elasticity of price or the marginal propensity to consume or the marginal cost. So you can put different interpretations on beta 1. And the data we have are x, y, the pairs of x and y, observations about them. And we will estimate the parameters beta 0 and beta 1, and we are going to denote them by beta 0 hat, beta 1 hat. Remember, we used to put hat on top of the parameter to represent its estimator. And of course, the estimators are known. That is, you must be able to calculate them from the data. That's the definition of requirement for an estimator. But they are random. That means if you regenerate a new set of data, then those numbers could be different. So they are known and random. And they will have their own sampling distribution. So using their sampling distribution, we can calculate a lot of things, right? We are going to do that. We are going to apply the estimation theory on these estimators. And then the main question is, how do we estimate them? Excel, we will base our analysis on Excel. Excel uses the ordinary least squares estimator. Ordinary least squares estimator, and we will delay. I'm going to explain the OLS later. For a while, for now, we will just assume that some estimators are given, and I will first show you what we can do with those estimators. Okay, then it will be clear later why we chose that as an estimator, right? As our estimator. Okay, I'm going to do it that way. So then let me show you how to do it on Excel. Here, there are 12 observations. These are exactly the same numbers that I used on the slides. So there are 12 numbers, and I would like to do regression analysis on Excel. Then it's simple. Data, you click Data tab, and click Data Analysis tab button here, Data Analysis tool. Then, and among these many options, choose Regression. Regression, click, and input Y range. Remember, Y is what's determined by X. So in our case, X is independent variable is output, and then Y, the dependent variable, is cost. So when you choose how much to produce, then the cost will determined by that. And I will check this. label, and I'm going to check this to show you line fit plot. So it will show scatter plot with a trend line. So I will click OK. So simple. Label means the first line is the label, and I'm going to show you the scatter plot. So OK. Then this is the results. First, let's look at the scatter plot. So blue is the same scatter plot you saw from the slide, and red is the predicted cost. How you predict, and the red is obviously a perfect straight line. So perfect straight line is the result of the regression line. So basically, the regression line is to making a straight line, the trend line on the scatter plot. So that's exactly the same thing you observed from slides. You saw from the slide. Okay. So this is what you do. Let me delete it. And then this side is, there are a lot of things going on in here. So let's look at this. So I'm going, the last one is not important. I'm going to delete it. So we will look at these three tables. So the 90, those are repeated. Same thing. I will delete them. So these are the main output from the regression analysis. So our goal in this chapter is to study what this means. So we'll take more practical approach. So I'm going to show you how these are derived and how they are related to what we learned. So actually the names are familiar, like p-value, t-stat. You know what they are. Standard error, coefficients, right? And lower 95%, upper 95%. I believe you guess what they are. They are, yes, right, they are confidence interval. Lower confidence limit, upper confidence limit at 95% significance level. Like confidence level, excuse me. And there are like standard error, observations, and basically we can understand many of them. So that's the goal. We try to understand, and I want you to be able to interpret those numbers later when you need to do it. Okay. So this is the result, exactly same result. I just rounded up. Same result, and we will kind of cross out if you after explaining what they are. Okay. Okay. So then, for now, as I said, for now, we will take the results as given. I'm going to explain how the results are calculated. But for now, I will just take them as granted, and I will first show you how we can, what kind of properties this estimator has, like confidence interval hypothesis testing. And also then, I will show you how we can utilize those results to predict the dependent variable. And finally, we will do additional analysis to check the accuracy of your analysis, how good the model is. So measure the accuracy of the analysis, how good the model is, how if the model is correct or not. So after explaining how we use them, then I will come back to the estimator and show you how to estimate them. Okay? So I'll continue in the next video. Thank you for watching. Bye.